Forward before I forget. Okay, hi everybody. This is Michael Tremmel. He is a postdoc at Yale, and he'll be talking about merging black hole binaries. You can go ahead and share your screen. And we usually wait for questions after, but if you have a question, you guys can type it in the chat. Okay, go ahead. Thank you so much.
Yeah, thanks for having me. I assume everyone can hear me all right. Hopefully the screen, you can see it. Yeah, I'm great. It was great to be invited. Yeah, I admit, I kind of thought that by Friday, things would have calmed down a bit with election stuff. I guess I was a bit naive, so still a bit anxious. A bit better though, 4 years ago, I actually gave a talk the day after the election, actually here in New Haven at Yale, which was interesting to say the least, so a little bit different this time. But thanks everyone for coming for this and for having me. So yeah, I'll be talking today about supermassive black holes in merging galaxies. And the movie that hopefully you all see playing right now on the screen illustrates more or less the overall point that I hope to make in this talk, is that supermassive black holes can actually experience a wide variety of dynamical evolution as a result of mergers. We're seeing here a forming Milky Way mass galaxy. There's a black hole in the center, and you can see the black holes in white. There's also a black hole in the center of this galaxy that you'll see quickly merge with the central black hole in this galaxy as it goes around a couple times. And then you also see these black holes on these very wide orbits in the galaxy. And in fact, what we see is that black holes can experience a wide variety of orbits, everywhere from quickly merging with the central black hole all the way to never ever reaching the center, and then everything in between, slowly reaching the center after billions of years of evolution. And what I hope to convince you of is that this galaxy scale evolution of supermassive black holes in dynamically active galaxies is actually a really critical component if we want to understand, make predictions for, and do astrophysics with future gravitational wave detectors. And also, as I'll mention near the end of the talk, actually can be an interesting probe of dark matter physics as well. Right, so just for a quick, motivation here, hopefully many of you are aware of the relationship that exists between black holes and their host galaxies, the famous M-sigma relation that I'm showing here, that larger galaxies tend to host larger supermassive black holes at their centers. And a lot of the interesting work to be done on the astrophysics side is understanding more or less how this relationship comes to be and how it evolves over time. Right, and one in particular way in which we think that this is interesting is that these black holes are, not only is their growth controlled by their galaxy, but through feedback processes like is shown here in these observations, they can affect and are actually a critical component of the evolution of their host galaxies. And in fact, not only are they important for massive galaxies, as is traditionally thought, but we're also seeing in simulations and in observations, they can also be important for low mass galaxies as well. So across the board, black holes are a critical component that we really don't understand a lot about. And our lack of understanding, I like to think of as, in part, that we have a lot of bias in how we see black holes, how we detect them, how we measure them in even the local universe. So this is a plot from recent work by Amy Raines and Marta Voluntari, showing the relationship between the black hole mass and the mass of their host galaxies, but with different black hole populations. So these bluer points up here essentially show the points I showed in the previous figure. These are black holes that are measured and detected through the dynamics of nearby stars in the nucleus of their galaxy. These are quiescent black holes in typically bulge-dominated or elliptical galaxies. But this itself, right, having one way of detecting and measuring black holes, we actually see a bias in this if we expand our view. And these points down here are measured black holes from active galactic nuclei from using broad line regions to determine the mass through the gas kinematics nearby the black hole. And so what we find is that we have to be careful about our limited view of black holes based on our limitations for observations. And as we think about trying to solve this scientific problem of how do black holes and galaxies co-evolve, I love this cartoon from Marta Voluntari's 2012 review. it kind of comes down to understanding, do black holes and galaxies evolve together over time? Do you have periods where one growth dominates over the other, either earlier or later? And a lot of this hinges on our ability to not only measure black holes and scaling relations at redshift 0 and nearby universe, but all the way out to the early universe. But as we go further away, of course, that fear that you're looking at a very biased and limited population really becomes more important. As you go to higher redshift, you're only seeing the biggest, brightest, actively growing black holes. Those are really the only things you can measure. And so that becomes a problem if you want to understand the demographics of black holes more fully and how they evolve over time. And that's exactly where gravitational waves come in. So I'm sure many of you know about LIGO, detecting gravitational waves from stellar mass black holes. And of course, LISA is one of the main future detectors that has been talked about, with a set launch date about 2034. LISA will be space-based, and so LIGO, as I say here, has 4-kilometer arms, while LISA will actually have 2.5 million kilometer arms by which to detect gravitational waves. And so what LISA is really doing is detecting gravitational waves from a whole different set of sources. While LIGO is focused on stellar mass black holes, LISA will be focused on supermassive black hole mergers. And this new gravitational wave window is really important. And LISA in particular, I think, has a particular chance of giving us a lot more information about black holes. So this plot here is showing the sort of discovery space of LISA as a function of redshift on the y-axis and black hole mass, or the combined mass of the two black holes on the x-axis. And what we can see from this plot is that LISA will be sensitive to black hole mergers, essentially measuring the mass of black holes and detecting these black holes, even in this era where we expect them to be forming for the first time. So this redshift of greater than 10 or so, where we're looking at essentially seed mass black holes that can really constrain how black holes form, how these supermassive black holes form in the first place, which is still not well understood. And it'll also be able to reach out in what I like to think of as the era of black hole growth, as the black holes are growing with time, ramping up to reach billions of solar masses, getting to be those very bright luminous quasars we see at redshift 7 that are very special, but also just in general, the overall population of black holes is growing over time out to cosmic noon. This is going to be LISA's bread and butter, these lower mass black holes that are actively growing in these lower mass galaxies that are merging at high redshift. And combined with JWST and future X-ray telescopes like LINX, you can really begin to see that we have a chance of really revolutionizing how we understand the demographics of black holes over cosmic time. And of course, in addition to LISA, we have pulsar timing arrays, so measurements of pulsars in the galaxy that create even a larger effective arm when we're talking about detecting gravitational waves, a galaxy-sized arm almost. And so this really rounds out what's shown on this plot here, this multi-band gravitational wave universe that we're really seeing. While LIGO was the first at this high frequency band that focuses on stellar mass black holes, and with LISA and then with pulsar timing, we're getting to these lower frequencies that are measuring more massive black holes. And pulsar timing will be very complementary to LISA in the sense that it's more sensitive to really massive black holes at lower redshift. So again, rounding out our idea of really figuring out the total demographics of black holes across cosmic time. But all of that astrophysics that we want to do really relies on how we understand binary black holes and mergers. Where and when do black holes actually merge, and how does that give us a sense of the overall population of black holes and how they're growing? And so this is very model dependent. And to make predictions from LISA and to get astrophysics from LISA and from pulsar timing requires good theoretical models. So as an example of that, these are two theoretical models showing the distribution of sources detectable with LISA, predicting essentially how many sources will LISA detect in its 4-year mission as a function on the left of the black hole mass and on the right as redshift. And these different lines show different models for either how black holes are formed in the early universe or how they grow. And so this is just an example illustrating that, given a model, and recent detections, we can actually begin to constrain some of these models for how black holes grow and form. But all that, again, relies on trusting that for a given model, you're correctly determining when and where you expect a merger to happen. And the same is true for pulsar timing arrays. There's already been astrophysics that people have been doing with previously the upper limits and now this potential detection of this gravitational wave background from pulsar timing. It can tell you things like on the left, can begin to constrain the local relationship between black hole mass and stellar mass. On the right, it can constrain the local black hole mass function in the universe. But all of these things, all of these results are model dependent. And so that's what I really want to focus on in this talk is, do we understand how black hole binaries form and what important processes are we missing? And so the reason why this is so complicated is in part because to form a supermassive black hole binary and actually get a merger goes across a wide range of scales. So you start off with a galaxy merger that begins essentially with one dark matter halo with a galaxy inside of it, falling into a more massive dark matter halo, and then feeling dynamical friction and sinking to the center. So you go from, tens to hundreds of kiloparsec scales, and then down to, say, several kiloparsec scales as the galaxies themselves merge together and the nuclei of those galaxies bring the black holes in the centers together to eventually form a binary in the center of the remnant. And once that binary forms, then you have a lot of detailed dynamical processes, either interacting with nearby stars or gas, for that binary to harden over time and eventually get to the stage where you expect gravitational waves to dominate and you get coalescence. So that goes from, tens of parsecs all the way down to milliparsec scales. And so there's lots of stuff going on here, lots of scales to consider. This first one we kind of get for free with cosmological simulations. We know quite well, actually, how to calculate the sinking timescale of the halo within a larger dark matter halo. So that's actually pretty good. We analytically know what to do there. And then on the other end, there's lots of detailed modeling that goes into these predictions for how binary black holes might harden and coalesce over time. Detailed n-body and hydrodynamic simulations focused on binary evolution. That is very complicated, still very much a field that's active, but very separated. While this intermediate point, the formation of a binary black hole pair in the first place from merging galaxies, is often ignored or oversimplified in these simulations. And so what I want to argue, as I said in the beginning, is that this phase is actually really important, and it should be something that we need to consider and study in more detail. So typically, studies of galactic scale evolution of supermassive black hole pairs are done using idealized simulations, in part because when you have a single galaxy, you can run your simulation at very high resolution, and you can actually model the dynamics of the black holes very well. And so you can sort of create your galaxy in isolation, hand make it as a nice disk galaxy, and on the left, you can have a major merger with two Milky Way mass galaxies you ram together, and you see what the black holes do. So this is work by Lucia Meyer in 2007, showing that in at least some situations you can form very quickly a binary black hole from a galaxy merger. But on the right, as you begin to expand these simulations to include lower mass ratio mergers, you begin to see that the mass ratio, the dynamics, the morphology and properties of the galaxies themselves end up making a big difference. And sometimes you get black holes that do ultimately fail to sink to the center of their new galaxy. And so things are complicated. And in addition, in reality, you don't have an isolated galaxy, but you have a galaxy embedded within an evolving cosmological environment. And indeed, these are some simulations run recently published results where you have a cosmological simulation at high resolution, and they've embedded black holes in the simulation and looking at what their dynamics look like. And so what they see is that indeed the black holes often have a wide variety of orbits, in part because these large-scale torques that are taking place within the galaxy as it's responding to gas accretion and mergers and large-scale torques from the environments and all that stuff. And so every scale on this matters when you're talking about the dynamics of black holes within galaxies. And so the one way to really do all this stuff self-consistently is to model these black holes and their dynamics within a cosmological simulation, where you have naturally evolving cosmological environment, growth of a halo happening over time with mergers and gas accretion and all that stuff. The problem, of course, is that simulations like this have, because they're so big and so complicated, have limited resolution and often pose problems when you're actually trying to understand black holes using these simulations. And so that's where my simulations come in, the Romulus simulations, which we're done with a focus on overcoming a lot of the simplifying assumptions people often make with black holes, supermassive black holes in large-scale cosmological simulations. So Romulus is a suite of high-resolution simulations. You can see the resolution on there. It's basically on par with the state-of-the-art large-scale simulations. A few hundred parsec resolution in terms of gravity, even better in terms of hydro, 10 to the 5 solar mass resolution. So these simulations can resolve low-mass dwarf galaxies quite well, and they overcome a lot of the simplifying assumptions. As I said, with black holes, we have early seeding of black holes. We actually follow the dynamics really well in the simulation. I'll talk about that in a second. And the simulations come in two flavors right now. Romulus25 is the one I'll be focusing on today, is a uniform volume simulation, a 25 megaparsec per side box with thousands of galaxies in it. And then Romulus C, which I won't be talking about, but is still cool, is a galaxy cluster simulation. So a large halo that's a zoom-in simulation focused on just on that one halo. So to go into a little bit more detail with what sets Romulus apart, in particular with respect to this work I'll be talking about, the first thing is how we seed the black holes in Romulus. So the black holes are formed in the simulation. Again, we can't actually resolve the actual formation sites of these black holes. What we can do is say, okay, well, when gas gets very, very dense and yet remains pristine in the simulation, then we form a black hole there. So you're sort of pinpointing the regions of particularly high density and low metallicity, which naturally gives you an epoch of formation that takes place within the early universe. So on the plot here, I'm showing that the distribution of formation times in the simulation for black holes, and we're forming them in early times, typically in low mass halos, more in line with what you'd expect in real life. Black holes form early on, they form in low mass halos. And in particular, because we can actually resolve those low mass halos, and the black holes exist at early times and are allowed to exist in whatever halo they're formed in without any assumptions, we're also sensitive to the exact type of mergers that LISA will be best at detecting, these low mass black holes in low mass mergers. That's going to make up the bread and butter of LISA detections, which is important. Now, the other really critical feature, as you might expect, is the dynamics of the black holes. Right? That's going to be the focus of this talk, really. And for this, we've developed I developed as part of my PhD thesis actually a model for accounting for resolution effects for dynamics. So the main challenge with large-scale simulations like this is that dynamical friction, which is the main thing causing black holes to sink to the center and remaining stable at the center of galaxies, is unresolved for the most part. And so using a subgrid model I developed, we're able to actually resolve that dynamical friction well. So you account for that unresolved dynamical friction and apply it to the black hole, and you get more realistic orbits. So what I'm showing here is a test simulation. You have a black hole in an isolated dark matter halo, and without any correction, the cyan line there, you get a very prolonged evolution because dynamical friction is not efficient. But with the correction, you get something much more realistic, where the black hole sinks within a few giga-years, as we'd expect from the analytic solution. This is in contrast with what's normally done in these large-scale simulations, which is just push the black hole towards the center and force it to stay there. What this does is essentially teleports the black hole from a few kiloparsecs to immediately to the center, and you lose that galaxy scale evolution. And so that's exactly what we want to study, so we don't want to assume it doesn't exist. So we're able to actually study this large-scale, galaxy-scale evolution of black holes uniquely in the Romulus simulations. So given that we have these simulations that form black holes at early times in low-mass galaxies and correctly follow their dynamics, we can then ask, all right, where and when do we expect black hole binaries to form with respect to, to mergers. How long does it actually take black holes to find each other in the center of a galaxy? And so again, a caveat here is that we don't actually, I can't claim to say that we resolve the formation of a bound black hole binary. We can't resolve down to tens of parsecs. What we can do is find black holes that I call close pairs. These are black holes that get within 700 parsecs of one another and are mutually bound based on their relative velocity and their masses. So these are most likely, essentially the precursors to forming a binary, the dynamics of which we can't actually follow further beyond this point. So that's what we're studying in these simulations. So how often does it actually happen? How long does it take? And then as a corollary to all this, what I'll talk about is a population of wandering black holes that come out of this, the work we've done. So taking the Romulus volume, Romulus25, our small volume simulation, looking at all the galaxy mergers that take place, we can then look at the fraction of those galaxy mergers that actually result in a black hole merger within a Hubble time, or again, a close pair of black holes within a Hubble time. So this is that fraction is a function of stellar mass on the y-axis, or stellar mass ratio on the y-axis, and the primary galaxy stellar mass on the x-axis. And so a couple things pop out. Minor mergers, less than 1 to 10 in stellar mass, never form a black hole binary in a Hubble time. And as you get to higher mass ratio, it becomes more common, and then even more common as you go to higher mass galaxies. So massive major mergers are the most easy to get a binary black hole out of. But even then, we're seeing that 2/3 to 3/4 of the time you do this, but that still leaves a significant fraction of these mergers that still never actually have a black hole binary form after the merger, which is interesting. So lots of mergers commonly never form a black hole binary. They never get to become close pairs, and will be these wandering black holes I'll talk about in a little bit. But the black hole pairs that do form, the close pairs that do form in the simulation, we can ask, how long does it take to make those close pairs? So this is a plot of the cumulative fraction of those close black hole pairs, the precursors to binaries, as a function of how long those two black holes have spent at less than 10 kiloparsec separation, so a few kiloparsec separations, galaxy scale separations. And what we can see from the black lines is that the overall population, there's about a quarter of them or so end up having, only forming a binary after gigayears of evolution within their host galaxy. So that's a significant delay time. And in fact, if we look at black hole pairs that form at low redshift, the majority of those are coming from these sort of leftover black holes that have taken billions of years to reach the center from their precursor merger that happened, again, several billion years ago. So again, how we understand the connection between galaxy mergers and the actual binary formation and eventual merger is very different here. That there's significant delays that are occurring. And to get an idea of why this is happening, we can take two examples. This first one I'm showing here is an example of a galaxy merger that results in a close pair within a few 100 million years. Over that same time scale, at the same time, roughly the same redshift, roughly the same mass galaxy, we have a merger that results in a black hole that takes about 1.5 gig years to reach the center. And the difference between these two kind of becomes clear if you look around that secondary black hole. At the top, that black hole always has a galaxy around it. You can always see this core left over by a once more massive galaxy that's been mostly stripped away, but retains that stellar core, stellar nucleus in the center. While at the bottom, that black hole is essentially left on its own. The galaxy that hosted that black hole was tightly disrupted in the process of merging with the galaxy. And so what we see is that the difference really is the morphology and mass ratio. When you have a major merger that also has the secondary galaxy maintaining a dense stellar core, it's able to survive the dynamical interaction with the merger. It's not going to become tightly disrupted. While the lower mass ratio galaxy mergers that don't have as dense of a stellar core do become tightly disrupted and do end up resulting in this prolonged evolution. So we can see this in action in this movie here. So this is, again, that same forming Milky Way mass galaxy. That galaxy that I pointed out at the bottom, that circle, you see this it's being torn apart by this interaction. This tiny little puffy red galaxy is being ripped apart as it's interacting with the main galaxy. And the black hole is just another star essentially in this galaxy, and it's being torn apart along with everything else. And then as that galaxy continues, that black hole is basically on its own. And this is even a more extreme case than what I showed before. The black hole is on such a wide orbit, it's never going to reach the center. It's going to wander for billions of years, all lonely and sad as a wandering black hole in the halo of this galaxy. As we see, this is actually a common occurrence. But right, we can see this more quantitatively by looking at the cumulative fraction of close pairs as a function of how long it takes them to form, how long they spend at 10 kiloparsec separations or less. On the left is the time relative to the dynamical time of the galaxy, and on the right is the time in gigayears. And in both cases, no matter how we cut the times, if we cut the population of mergers based on density and mass ratio in quartiles, we see that the most dense, highest mass ratio mergers are the ones that form binaries the fastest. These are the ones that avoid tidal disruption, where the nuclei can then bring the black holes together and then form a binary. So it's really the nuclei of the galaxies that need to survive that depend on actually forming a binary relatively quickly. Now, what are the consequences of this? And we can start to see this if we actually directly look at the simulation data. So for all the mergers that we have, the pairs that form in the simulation, we can trace those pairs back to their original galaxies and the redshift infall of those galaxies. So we can trace them back to the time at which, the redshift at which the host galaxy first fell into the main galaxy. And then using the typical analytic modeling that's used, derived from cosmological simulations, we can estimate roughly what would your typical semi-analytic model predict for the time of binary formation. And that's what we see in blue here in the simulation. While in orange, we see that the raw data from the simulation, given a satellite infall redshift, when does the pair actually form? What is essentially the minimum time to form a binary? And at high redshift in particular, we see that a lot of these prolonged mergers are not captured in the semi-analytic modeling. Again, the blue points represent what's typically used in models to make predictions for gravitational wave detection. So, what we've done, is we have a small volume simulation, so it's hard to really make a concrete prediction for semi-analytic or for gravitational waves because it's so small. We can't run it multiple times, but we can use this simulation to implement a delay time into these semi-analytic models. So that's exactly what we've done. So the semi-analytic models, they take halo merger trees, and they take that and they analytically estimate, okay, well, if you have mergers of dark matter halos, how does that translate to galaxies, and then how those galaxies translate to black hole mergers. And then they predict this population of binary black holes and how those binaries should evolve over time and when they should merge and all that. And what we've done is implement different delay times to these to the formation of binaries. So we've included dynamical friction that the galaxies feel, so the delay time to essentially finish a galaxy merger. There's a delay time on smaller scales at like 100 parsec scales that has to do with dynamical friction to finish forming your binary. And then finally, there's this kiloparsec scale delay time that we've implemented from our results from Romulus, essentially assuming that the distribution that we see in Romulus is true for all galaxies. And we see what the results are. So the plot on the right is the predicted number of detected black hole mergers as a function of redshift for these different delays. And so we can see a couple things from this. The top plot is for massive seeds. I'll focus on that first. So these are models assuming that black holes form, at 10 to the 4, 10 to the 5 solar masses, essentially from direct collapse or from the collapse of a nuclear star cluster at high redshift. The red line is what we predict without any sort of large-scale delays, so only binary evolution. Essentially, nothing happens between the merger of two halos and the formation of a binary. And then we see a dramatic decrease in the amount of high redshift mergers we predict if we include even one of these delay times at large scales. And then this delay gets further if we include the Romulus delays shown in blue. So the difference between including these delays, these kiloparsec scale delays from Romulus, is about another factor of 2 to 3. Right? So these large scale delays are important for determining the redshift distribution as well as the total number of black hole binaries and mergers you expect to be able to detect with LISA. And the same is true actually for low mass seeds. So at low mass, when you form black holes from like population 3 stars, your limiting factor is actually more so how quickly your black holes grow. And so in fact, the solid lines here represent the actual predicted detections. This is actually not very sensitive to any of these other delay times, but it is sensitive to these kiloparsec scale delays. So while typically low mass seeds are more sensitive to what we assume about how fast black holes are able to grow and get massive enough to actually be detectable, even in that case, this kiloparsec scale delay time is important, and again, decreases the number of mergers we expect by a factor of 2 or so. So this is important. In addition, right, what these delay times do is push back the merger event itself from the parent galaxy merger, right? So what we're looking at in both of these plots, and the massive seeds one is a bit more clear cut. You can see that on the top. Is the distribution of times between the merger of the galaxy and the merger of the black holes, taking into account both all the binary evolution, but on the left, those two lines are without these large-scale delays, and on the right is when we include all those large-scale delays. So when we include the Romulus delays as well as these other delay times that we've included in these simulations, there's a massive shift. And the shift is also there for the low mass seeds as well. You go from having a time between, on the order of a few 100 million years on average to giga-years on average between the galaxy merger and the merger of your black holes. And that means that, when you're trying to do these multi-wavelength, multi-messenger observations of black hole mergers with, to complement gravitational wave detections, the host galaxies to merger events are not going to be merger remnant galaxies. These are typically going to be galaxies that have gone through a merger 1 or 2 billion years ago, but have only just gotten a black hole merger recently. So this changes, again, how we want to do the astrophysics and some of the follow-up observations from these galaxies. And Marta Volontieri has also done this in her recent paper using a cosmological simulation as well. So this is becoming a common viewpoint. Now, so the corollary to all of this, right, is that it takes a long time for black holes to reach the center of galaxies. And so that means at any given time, a massive galaxy that has a rich merger history can have off-center black holes in it. These wandering black holes are away from the center. Maybe they'll get there in a few billion years. Maybe they won't. And this topic of black holes off-center from galaxies is something that has been looked at from the theoretical side using both semi-analytic modeling and cosmological simulations. For the semi-analytic modeling, often the case is looking at this idea of gravitational recoil. When two black holes merge, they get a kick from gravitational waves that can push them away from the center. That's not what I'm talking about here, because we don't model those kicks in the simulation, because we don't model the actual mergers of black holes, and certainly we don't model the spins of the black holes. Rather, what we're looking at here is the delay time just because the black holes have been deposited on a very wide orbit. And in fact, if we look at massive galaxies, and in this case, Milky Way mass galaxies, in the simulation at redshift 0, these galaxies have several black holes on average off-center. So the typical isolated Milky Way mass dark matter halo, its galaxy hosts about 5 black holes on average within 10 kiloparsecs of the center. That's the central black hole plus 4 wandering black holes within the galaxy on average. And it turns out that how many of these black holes exist doesn't actually depend very strongly on the recent merger history of the galaxy. So if we split up the galaxies based on their morphology, disk-like versus elliptical, or whether or not they've had a recent merger or not, the distribution of wandering black hole numbers doesn't really change very much. That's what I'm showing on the left here, is the fraction of halos is a function of the number of black holes that they have. And that's because these black holes that are wandering were put into the halo at much earlier times. So the recent evolution doesn't really matter that much. This isn't a recent merger typically that has resulted in these wanderers. Now on the right, I'm showing that these wanderers are typically found in the stellar halo and not the disk of the galaxy. So this is the probability density of finding a wanderer as a function of the angle relative to the disk, the inclination angle to the disk. So given a random distribution, we'd see something like the black line there, while what we really see is bias away from the disk. So these black holes are not within the disk of the galaxy, and that's because, right, if they were in the disk, they'd feel much stronger dynamical friction and therefore make their way to the center much more quickly, and they wouldn't be around anymore at redshift 0. So these are black holes in the stellar halo of massive galaxies. Now, widening our view a bit. Oh, this plot came in much lower resolution than I thought it would. So if we look at the general population of galaxies in the simulation as a whole and plot the number of wandering black holes as a function of halo mass, we see that it scales more or less linearly with halo mass. The more massive halo, the more rich merger history, the more minor mergers you have, the more you get these deposited black holes on long orbits that will never sink to the center. And most of these black holes tend to be within 0.1 R200 of the halo in most cases. Now, an interesting thing to think about is that how much actually mass is in these wandering black holes. These black holes are probably going to be really hard to detect, which is why we haven't seen them yet, or at least we actually have seen some of them, but they're hard to see. And so it becomes interesting to think about, how this is biasing in a different way our demographics of black holes. We're probably missing a lot of these wanderers if they exist. And indeed, if we go to high redshift, if we look at the total accreted mass within a galaxy that's tied up in centrals in black versus these wanderers, and focus on the cyan dots, the cyan points in this figure, we see that as we get to redshifts of 2 or so and above, these wandering black holes that are at least 700 parsecs or more from the center of the galaxy end up almost dominating the total accreted mass budget of these galaxies. Now, as time goes on, these black holes will eventually sink to the center, and the central black hole will begin to grow more and more rapidly, and as it accumulates mass, it becomes more dominant. So both those things put together mean that by redshift 0, the central black hole still dominates the total mass budget. But at high redshift, that's not the case. So the high redshift black hole population might be quite different. It might be quite hard to detect. That's the prediction we're making in these simulations. So the question is, can we actually see these wandering black holes? And the first thing I want to think about is, could we see them in our own galaxy? Right. So the challenge, of course, is that if they're in the stellar halo, on average, these black holes are going to have very low luminosities. But in the Milky Way, at least, we could detect these kinematically. And one interesting way that we might be able to do this, and this is work done by Anna Banaka in 2019, is through their influence potentially on stellar streams. So they found this interesting result that, if you use Gaia data to map out these stellar streams, you find these interesting holes and spurs within the stream. And if they model dynamically what you would need to create this morphology, they find that they need some very dense, very massive object. And none of the known globular clusters in the Milky Way fit the bill. They fit the bill in terms of size and mass in some cases, but they don't actually have the right kinematics to have taken them through the stream in this way. So this is interesting. It could be pointing to something very massive and dense like a black hole. That's one interesting way of doing it, but it'd be really hard to know for sure what's happening there. Now, if we go out of our own Milky Way, one kind of exotic way that we could detect these wandering black holes is through this lensing effect. So there's a few known very razor-thin milli-arc-second lensed arcs. So these are galaxies that were lensed at high redshift that create very thin arcs on the sky. such that if a black hole somewhere in the universe came between you and that lens, you could actually see the perturbation that the black hole would make on that very thin lens. Now we actually did the calculation with the Romulus black hole population, the wandering black hole population, and we estimate you need, you know, thousands of these arcs to detect one of these black holes. And right now we know of a handful, so it's probably not really feasible to do. But it turns out that these black holes are not always dark. So what we're looking at here, and actually I said this is all work that's preliminary that is being done by Angelo Ricarte, postdoc at Harvard. I'm working with him on this. So what he's done is looked at the average bolometric, the total bolometric luminosity on average for wandering black holes in galaxies compared to the central black holes. And so at low redshift, the total black luminosity is, you know, order of magnitude or more below the luminosity of the central AGN in most cases. But as you go to high redshift, again, you begin to see that these wandering black holes make up a substantial amount of the luminosity. And even if individually they're not bright enough, you might be able to detect their presence using stacking techniques or things like that. But in fact, some of them might be bright enough to detect individually if you can actually resolve the two sources. And so this brings up this idea of dual AGN, where, you know, typically we think of dual AGN as a result of merger events, and indeed we see the presence of dual AGN in Romulus. This is one galaxy example from my 2017 paper of a dual AGN that has several different phases of dual activity as the merger progresses. And so as the black hole makes its way gradually to the center, you know, it has maybe 1 billion or 2 years to get to the center and has many options to be potentially quite luminous as it reaches the center of the galaxy. So this could be an interesting thing, especially if we think of our increasing abilities to observationally detect these black holes. And I know Julie Comerford at Colorado and others like Scott Barrows have done a lot of work already on detecting this population of wandering black holes in galaxies. And so, you know, another way of thinking of wandering of dual AGN is that you're seeing something that's off-center, a wandering black hole. And as we go to higher redshift, as we improve our ability to differentiate different sources at high redshift, this could be a really interesting way to see these wanderers that we're predicting in the simulations. Now, another thing that's come up recently in observations is a rich population of wandering black holes in dwarf galaxies in particular. So on the left, I'm showing some observations of AGN, off-center radio AGN, observed by Amy Raines in a recent paper. And also Scott Barrows has done some work on hyperluminous X-ray sources that are also off-center that might be massive black holes accreting in these galaxies. And so dwarf galaxies are an interesting laboratory. And indeed, Jillian Bellivari, using some high-resolution simulations, the same that employ the same dynamical friction model that we used in Romulus, has found that in our simulations, these are the marvelous dwarf simulations that Fra Munchi ran, and you can see that in her 2019 paper. In Jillian's paper, she explored these off-center black holes that we see very much similar to these observed off-center black holes in these low redshift dwarfs that are being detected. Now, black holes dwarf galaxies are really interesting for a different reason, in that, unlike more massive galaxies, they're dominated by dark matter. And this brings up another point, is that the dynamical evolution of these black holes, while I've already said depends on the merger properties of galaxies in lots of cases, because you need those stellar nuclei to bring the black holes together. But another factor that's particularly important for dwarf galaxies is the dark matter, because in dwarf galaxies, the dark matter is going to be what's going to dominate the dynamical evolution of black holes, especially on smaller scales. And so the reason why this is interesting is that one thing we know about dwarf galaxies for a while now is that many of them have cored dark matter profiles. This means that they have flat dark matter profiles relative to the cuspy NFW profile that we're used to from dark matter only simulations. Now you can form these cores from supernova feedback. It's been shown that explosive feedback that's prevalent in low mass dwarf galaxies create these flat cores naturally. And if you have these flat cores, Thomas Tomfel showed a couple of years ago that, and this has been an issue that people have been thinking about for decades, is that you do actually get this what's called core stalling, that the black hole will actually stall at the core radius of this flat dark matter core. And indeed, if you think of it the other way, if you start a black hole at the center, it can then also very quickly deviate from the center given one of these core dark matter profiles, because dynamical friction is weirdly inefficient in such cores. And this could be a problem for actually forming binaries in the first place at all redshifts in dwarf galaxies. But there is actually one other way to form cores, and that's through more exotic dark matter physics. So we actually ran a smaller version of Romulus, a smaller volume with the same physics, same resolution, with self-interacting dark matter. So this is dark matter that is able to interact with itself through some unknown force, and through that collisional interaction creates large core profiles. And in this case, in the simulation, in the plots on the left, we're showing the inner dark matter mass as a function of time. So these are creating large cores, larger than you'd expect from supernova. And over time, the dark matter is decreasing in the center. And as that's happening in this particular galaxy, the distance from the center of the black hole is also increasing. So as I said, as you form these core dark matter profiles, in this case, through dark matter physics, exotic dark matter physics, it's affecting the dynamics of the black holes. You're less likely to actually see black holes at the center of, in this case, a lower mass, on the high mass end of dwarf galaxy, let's say. And on the right, what I'm showing is the distance of different black holes as a function of the stellar mass. And so again, in the SIDM case, compared to cold dark matter, once you get to these dwarf galaxy scales, where the black hole relies more heavily on the dark matter for dynamical friction, you get a lot more off-center black holes that are having a hard time reaching the center, and then also will potentially have a hard time merging at higher redshift as well. So again, all this is saying is that further detection of wandering black holes, as well as merger rates, might depend a lot on possibly interesting dark matter physics beyond just core profiles, but even self-interacting dark matter and things like that. Now, self-interacting dark matter actually has another effect. And this is work done by Akasha Cruz, a grad student at University of Washington, who's actually, I believe, on the job market this year for a postdoc, just to throw that out there. Akasha looked at a few Milky Way zoom-in simulations using the same physics as Romulus, but run again with CDM versus SIDM. And what she found was that because self-interacting dark matter doesn't require supernova feedback to form cores, it can begin acting at higher redshifts before any stars form. And so you actually get a very high redshift. At redshift 6, self-interacting dark matter is having an effect on the gas density. So you have less very dense gas. This is on the right, the probability distribution as a function of gas density. You're less likely to have very high density gas. And so based on our formation model for black holes, you're less likely to form the black holes in the first place. And so the self-interacting dark matter simulation forms less black holes. The black holes go through less mergers because there's less of them around. And they also grow less rapidly because the early growth is actually dominated by mergers at high redshift. So self-interacting dark matter can have important consequences for how black holes are growing and how often they're merging because they don't form as often potentially. So all this is saying that dark matter physics actually might come into play in really interesting ways when we're talking about the dynamical evolution, the growth evolution of black holes over time, and what we can learn from future gravitational wave detections. So just to summarize, right, the main points, if you take away anything from this, is that kiloparsec scale, galaxy scale, dynamical evolution of black holes is really important. It's a critical ingredient to understanding black hole merger rates, to making predictions for LISA and pulsar timing arrays. And wandering black holes are interesting. I hope we can detect them in more detail. Current work right now from my end is working on dual AGN in more detail and trying to make more detailed predictions for that. And yeah, dark matter could be really interesting to look at in this context. So with that, I'll thank you for your time and take any questions.
Thank you so much. That was great.